All right, we are ready for the next talk in the session. Shunhua, Jiang.
Thank you. So I'm Shunhua, and then this is joint board for Group Grade, and Omri Weinstein is my advisor, who is also in the audience. Okay. So today I'm going to talk about our new Fox result, which is the complexity of dynamic least squares regression. But before I move on to the dynamic problem, let's first remind us of the canonical least squares regression. So this is also called L2 regression. And then Diksha covered the harder LP regression in her previous talk, but today we're only going to focus on the L2 norm. So in this problem, our goal is to find the vector x that minimizes the L2 norm of ax minus b. And we should think of A as a very thin and tall matrix, and it has all the data. So the least square regression problem has many applications, and it's the simplest way to model some data. So basically, if you have a lot of data points, this will give us a linear model that fits the data. Okay, and the L2 norm least squares regression is very simple because we have an exact solution to this problem. So the exact solution is given by this normal equation where it's computed by some inverse times A transpose times B. So you can compute this exact solution by using fast matrix multiplication. So if you compute this from scratch, it would take n times d to the omega minus 1 time, where omega is the fast matrix multiplication. It's about 2.37 right now. And the bottleneck to compute this is to compute this matrix multiplication inside the inverse. Okay, but often this is still too slow for many modern data analysis applications. And often in real life, we're happy to just get an epsilon approximate solution. So here we will define an epsilon approximate solution to be vector x such that the norm of ax minus b is at most 1 plus epsilon of the optimal value. And if we are happy with epsilon approximation, then we can use the sketch and solve paradigm. And the best running time right now is nearly linear in the input size. So right now it's basically nza times log 1 over epsilon. Note that the dependence on epsilon is also logarithmic. Okay. And now in this paper, we consider a dynamic version of the least squares regression problem. So in the dynamic version, our goal is to maintain an epsilon approximate least square regression solution where we allow insertions or deletions of the rows and the labels to our data matrix. Okay. And our goal now is that whenever we receive a new update, so it can be an addition of a new row or a deletion of a row, we wanted to minimize the amortized update time. And so now we think of there are in total n iterations, and we should think of n as being much larger than d. So think of n as some big polynomial of d. And this models some dynamic data applications. For example, in continuum ML, which is more complicated than this, this is the simplest model where we already trained some model based on our existing data, but we're still actively collecting new data. And we wanted to incorporate the new data into our model without retraining our model from scratch each iteration, which could be too expensive. Okay, and then there are some important settings that we consider in this paper, and I should define them right now. The first is incremental versus fully dynamic. So we call a problem, call the updates are incremental if we only receive new rows. So we only collect new data, but we never throw away our existing data. And the harder update would be a fully dynamic update where we are receiving both insertions and deletions of the rows. Okay, and the second difference is between oblivious updates and adaptive updates. So for oblivious updates, we can think of it as in the beginning, even though we don't know what the updates are, but they are fixed and that they don't depend on what our algorithm do. But adaptive updates, we allow some adversary to choose the next update based on the solution that's generated by previous outputs. So these two updates are the same for the algorithm if the algorithm is deterministic. But if the algorithm is randomized, then the adaptive updates can be much harder because then your update either in the next run could depend on the randomness that you use in your algorithm. So it could break some independent that we might use in the analysis. Okay. And before I go to our result, let's first say what are some existing algorithms for this problem. Well, this problem has a long history. So it was already studied in the 60s by the control people, so by the Kalman filters. So if we wanted to just maintain the exact solution of this problem, we don't need to compute the inverse from scratch in every iteration, as that would take like n to the omega time, d to the omega time. We can just use Woodbury identity for matrix inverse, and it would give a time per update of d squared. And this is a deterministic algorithm, and it's exact, so it works for the hardest fully dynamic and adaptive updates. But if we're happy with just getting an epsilon approximate solution, then there are more recent results that use online row sampling, where they don't keep all the big data matrix, they just sample much fewer number of rows. So in this paper by Cohen, Musko, and Petrocki, where they show that they can maintain an epsilon approximate solution by sampling d times log kappa over epsilon squared number of rows, where kappa is some condition number of the data matrix. And I should say, and their algorithm only works for incremental and oblivious updates. And I should say that because their paper didn't really care about the least square regression problem, they cared more about maintaining a spectral approximation of the inverse matrix. So if we just apply their algorithm directly, it will still take d squared time, but this time is to compute the sampling probability. I will say more later when I go to the details. And then more recently, there's a new paper by Biberman et al., where they showed how to generalize this online row sampling framework under adaptive and still incremental updates. But here, they will lose a linear dependence in kappa. So here, they will need to sample more number of rows. They will need to sample d squared times kappa times log kappa over epsilon squared number of rows. And because they still compute the sampling probability, it still takes d squared time. So the question we ask in our paper is, can we achieve better time? Can we achieve of order d time per update? And can we achieve nearly linear time during all iterations? And we answer this question affirmatively. So our upper bound shows that there is a data structure that can maintain an epsilon approximate least square regression solution under oblivious incremental updates with a total running time of nd plus d cubed times some polynomial of 1 over epsilon. We can also make this algorithm work against adaptive but still incremental updates. And we still get the first nd term, but we will lose something in the second term. It will become d to the fifth instead of d cubed. Okay. And since we consider the situation where n is much larger than d, and then if we also assume that epsilon is some small constant, then this will give our desired amortized cost per iteration that's of order d. So this improves from the previous d squared cost per iteration. And I also wanted to add, even though I write nd here for this talk, but it's actually nz of an, so it's nearly linear time during all iterations, and that matches what we get in the static case. And I also want to mention that I don't write any condition number in these upper bounds, because we improve the number of sampled rows for this previous paper from a linear dependence in the condition number, where the condition number might be polynomial. We improve this to a log dependence. So I'm just hiding the log inside this O to the notation here. Okay, so now if we look at this upper bound again, there are two places that don't seem super tight. There seems to be still some room of improvement. First one is that we will have a polynomial dependence on 1 over epsilon. But if you remember a few slides ago, I showed that the best algorithm for the static case only have a log dependence on 1 over epsilon. So is it possible to improve this? And the second place that doesn't seem super tight is both of these two algorithms only work for incremental updates. So they don't, even though we can work against adaptive updates, but it's still when they're only incremental. What happens if the updates are fully dynamic? Can we still get of order d update time? But unfortunately, we have some lower bound results that show that both of these two questions are not possible. So our lower bounds are all conditional lower bounds based on the OMv conjecture that I will say in more details when I go to the later sections. But under the OMv conjecture, we show that if we want a data structure to maintain a very high accuracy least square regression, a 1/poly and approximate least square regression, even under the easiest oblivious and incremental updates, then this would take d squared time. So it means we cannot possibly get some running time that looks like d times log 1/epsilon, because that would break this lower bound. So this basically means we cannot improve that poly dependence on 1/epsilon to some log dependence. And our second lower bound result shows that if we want the algorithm to support fully dynamic and adaptive fully dynamic updates, then even if we just wanted to maintain some constant approximation, then this is already too hard. This would take d squared time per iteration. So it means we cannot generalize our upper bound to work for fully dynamic updates. So basically, this is a negative result to both of the previous two questions. Okay. So next, I will move on to more details of all these results. And my talk today will have 3 parts. The first part is the upper bound, but under oblivious incremental updates. And in the second part, I will say how we let the algorithm work for adaptive updates. And then in the third part, I will go into the lower bounds. So are there any questions for the results? Yes.
So Oblivious fully dynamic update is still possible?
Yes, we don't know whether there's an algorithm or there's a lower bound. It's still open. Okay.
Actually, sorry, can I ask?
Yes.
What's the best known for adaptive fully dynamic updates? Is there an obvious d-squared solution, or it's like?
Yes, there's the exact solution where you just update the normal equation by using Woodbury. That just takes d squared time, and it's exact, it's deterministic, so it works for any update.
Yeah, thank
you. Yeah. Okay.
Sorry, why doesn't that have an end?
Oh, this is amortized cost per iteration, and there are n iterations.
Oh,
it's d squared per iteration. Okay, so let's first go to the upper bound for incremental and oblivious setting. So let me first define some notations that I will use throughout this talk. So now we're considering incremental settings. So we assume that in the ith iteration, we're given a new row, which is denoted by AI, and a new label, which is just a number denoted by beta I. And our goal is to solve for this least square regression problem. So we will use capital AI to denote our data matrix up to the ith iteration. So we have the current I rows. And we'll use BI to denote our labels up to the ith iteration. Okay, and I first wanted to cover the exact solution because our algorithm will also use this in some way. So the exact solution just compute the normal equation exactly in each iteration. And the hardest bottleneck to update this normal equation is to update the inverse. If we do it naively, it would take d to the omega time to compute the inverse. But luckily, we notice that from the inverse that we already have in the previous iteration, this is just a rank 1 update. So we can use the Woodbury identity for matrix inverse. That basically says it suffices to just compute a matrix vector product in order to update this inverse. And this takes d squared time. So this is also the algorithm that would work for any update. Okay. And this is if we wanted to do an exact solution. But we are actually happy to just maintain an epsilon approximate solution. So what are some techniques that are used in the static case for just epsilon approximate solutions? Well, the standard technique is called subspace embedding. And then a lot of this is covered in the survey by David Woodruff. So for subspace embedding, if we are given a very tall matrix A, we can have a matrix S to compress this larger matrix A into a much smaller matrix SA. And we say that S is a subspace embedding, a 1 plus epsilon subspace embedding for the matrix A, if this SA matrix preserves the norms of A for any x. So if the norm of SA times x is a 1 plus epsilon approximation of the norm of AX for all x, then we say this is a subspace embedding. And if we have a subspace embedding for the matrix or matrix A and the labels B, then we can directly use that to get an epsilon approximate solution for the least square regression problem. What do? Is we just solve this smaller problem, this compressed problem from the subspace embedding, and then this problem is directly a epsilon approximate solution for the original least square regression problem. Okay. So what we wanted to do when we wanted to make this all dynamic. We wanted to make this work so we wanted to dynamically maintain some subspace embedding of our matrix A. And there are many different techniques that can achieve subspace embedding. One very widely used technique is sketching techniques, where it adds some random matrix. But the sketching technique is a little hard to dynamize because this matrix can be dense and it can depend on all rows of A. So what we use is this sampling technique that just samples some rows of A and it throws away the other rows that we don't keep. And this technique is much easier to dynamize. Okay. So next, let me go into what is this Larry score sampling. So for a fixed matrix A, in this slide, I'm going to define this Larry score sampling for a fixed matrix A. And on the next slide, I will say how to make it dynamic. So for a fixed matrix A, and let's call its ith row AI, we can define a Larry score for its ith row by this equation. So AI transpose times this inverse times AI. That's an illustration here. And it's also the diagonal entries of the projection matrix that's defined by A. And intuitively, what is a Larry score? Intuitively, a Larry score measures how important the ith row is for the row space of A. So if a Larry score of one row is 1, this means this row is very important. If we remove this row, then it will decrease the rank of A by 1. And if all the rows are the same, then they will all have the same importance. Oh, by the way, during this talk, I'm always going to assume that this matrix have full column rank, so its rank is D. So when the rows are all the same, then they all have the same Larry score and will be D over N. And the Larry scores have two main properties. One is that all the Larry scores are between 0 and 1. And the second is that the summation of them will become the rank. So basically, it's a way to measure how important a row is, and then all of them together, it equals to the rank. Okay, and what is the Larry score sampling? So it basically says if we sample the ith row with a probability that's proportional to its Larry score, and this over epsilon squared. If we sample a row with this probability, and then we keep this row with up to some scaling, and then we throw a row away if we don't sample it, then the sampling matrix D will give us an epsilon subspace embedding for A. Okay, and because we're sampling with probability that's proportional to the Larry score, and then we know the sum of the Larry score is D, so in expectation, we will sample roughly D over epsilon squared number of rows.
Are you
Yeah.
missing a log in also?
Yeah, there's log in somewhere. Sorry, I should write O2 here. Sorry. Yeah. Yeah. So like with high probability, there should be a log 1 over delta dependence if we want delta for your probability. Okay. And then this recent paper by Cohen, Musko, and Petrocchi, they showed how to make this Larry score sampling work in an online setting. So we can then define the online Larry scores, which is defined as the row, it's still the ith row, but the matrix in the middle is not the whole matrix. It's the matrix that we get up to the I-1th iteration. So it's our current matrix. And this online Larry scores is always overestimates of the true Larry scores. Why? Because according to the matrix order, matrix partial order, the smaller matrix is always smaller than the whole matrix. So these online Larry scores are always overestimates. And this is also one of the reasons from the upper bound side why incremental setting is much easier than the fully dynamic setting. Because in the incremental setting, we're always computing the Larry scores according to some smaller matrix. So they are always overestimates. But if you also have some deletion of the rows, then the previous Larry scores that you computed could be an underestimate, and it's a little harder to deal with. And because it's overestimates, we can directly sample with a higher probability. We can still get the subspace embedding guarantee all same as before. Okay, but the problem with the overestimate is that now the number of sampled rows is still the summation of all the sampling probabilities, so it's still the summation of all these online leverage scores. But they are overestimates, so we'll still need some upper bound on the sums. And this was shown by this previous paper where they show that we will just lose some log d kappa factor in order to bound the sum of all the online leverage scores. Okay, and the proof is actually pretty simple that I can cover this in this space. They just use this matrix fact, which says that the log dat of some matrix M with a rank 1 change is larger than the log dat of the matrix M plus this A transpose M inverse A. So if we apply this to the rows, if we take A to be the row and then take this M inverse to be this inverse matrix, then this value is exactly the online leverage scores. And then what they prove is that use this log dat function as a potential function, and then you just compute the difference from the nth iteration up to the 0th iteration, and we'll get the summation of all the online leverage scores. So the summation of all the online leverage scores is smaller than the log dat of your final matrix minus the log dat of your initial matrix, and that's exactly bounded by kappa to the by d kappa. So it's like so that's why we get this log d kappa factor here. Okay. So similar as before, in expectation, we will sample the summation of pi number of rows, and now this is d times log kappa over epsilon squared number of rows. I'm hiding some further log in the OH notation. Okay. So now, after we describe this, we're ready to describe the algorithm for Oblivious updates. So in the algorithm, we will always maintain a subsampled matrix, where the D is the sampling matrix according to the online leverage scores. And in iteration, when a new row arrives, we will first compute its online leverage score by using approximately by using the subsampled matrix that we already maintained. And then we will flip a coin with probability that's proportional to this leverage score. And if we get 1 from the coin, then we will add a scaled version of the row as a new row to our subsampled matrix, and we will update the inverse and the solution. And if it's 0, then we just throw away this row, and then we don't do any update, and then we still output the same solution. Okay, so now next let's bound the running time of this algorithm. So there are 2 steps that we need to care about. The first step is to compute the sampling probability. The second step is when we're performing the updates. So let's first bound the second time. So when we're doing the update, we can just use what we do for the exact solution. We just update it by using this Weber identity for matrix inverse, and this will take d squared time to do this update. And as we showed on the previous slide, the total number of updates is bounded by the sum of the online leverage scores, and it's bounded by d times log kappa over epsilon squared. So we just multiply these 2 together, and this gives us the total time for this update operation. And this is actually a smaller term. This is the second d cubed term in our final running time. And when n is much larger than d, this is a very small term. This is d to the little whole 1. Okay. So next, let's talk about the time for computing the leverage scores. So if we compute it directly, that's like if you don't do any trick, that's what it did in the first papers, this would take d squared time. Why? Because the matrix already have size d by d, and if we just wanted to multiply the matrix with the vector, it would take d squared time. But we can use this Johnson-Lindenstraus lemma to accelerate this computation. The Johnson-Lindenstraus lemma says that there exists some JL matrix J that is very, very flat. So it only have log n number of rows. And this matrix J can preserve the L2 norm of n number of fixed vectors. And we notice that we can write the online leverage score as some L2 norm. So what we do is that we let the algorithm also maintain a sketched version, a JL sketched version of the matrix. So now that instead of computing this product, which is like an n by n matrix times a d by d matrix times a size d vector, we compute something that's much cheaper. So we just compute this product. This is the matrix that we already maintain, and it only has size log n times d, and then we multiply that by a size d vector. So this only takes d times log n time. Actually, it only takes nz of ai time, but I'm writing d here just for simplicity. So this will give a total running time of nd times log n. Okay, and that's the first term that we get here. And the second term comes from all the updates, and this is how we get this program. Are there any questions? So this is all I have for the Oblivious updates part. Yes.
So when you update a tutor, you need to update this sketch matrix.
Yes,
too,
we
right?
need to update the sketch matrix too.
Is that like easy to see?
Yeah, so like it's the hardest part is still to update the inverse here. So you can just still use the blueberry, and
Oh,
it
okay, got
still boils down to like a matrix vector multiplication.
Right.
Yep.
I think I'm just like not getting it, but like, do you update the matrix that you use to compute these upper bounds on the leverage scores, or like is it A0 all the time, or you do update it?
You do update it. And
Okay.
because, yeah, this is something that I'm hiding under the rug. Because this matrix is some subspace embedding of your actual matrix, this will give some approximation to the leverage score. So you just lose some constant in the summation here, and this still gives you a good enough something.
Okay.
Yeah.
Thank you.
Okay. Okay. So next, let me move on to our upper bound for incremental but adaptive setting.
Sorry, can I ask a
Yeah.
question about so when you are making this update, how do you manage like the interaction between the randomness of, maybe there is nothing to manage, like you're doing something that depends on.
Yes.
Yeah.
Yeah, exactly. So that's what I'm going to put right here. Yeah, maybe let me go over this slide first and then see if that answers your question already. So next, let me move on to the adaptive updates. So first of all, if we're only considering Oblivious updates, then that would not be a problem because your updates are all just fixed. And if we're considering adaptive updates, it would be a problem when our algorithm uses randomness in it, and our algorithm does use randomness in it. And where does our algorithm use randomness? Well, there are two parts that we use randomness. The first part is when we are using this JL trick to estimate all the leverage scores. And how to make that work against adaptive updates is actually pretty easy. What we do is that we just make the JL estimate and overestimate. So we just increase it manually by some constant factor. So that makes sure that we always sample with a higher probability than what the exact algorithm would do. And whenever we actually perform an update, we will renew the JL sketch immediately and then never reuse it. So in this way, our JL sketch is never reused. We never really leak any information to the adversary. So this part is actually easy. And the hard part is how to make the sampling itself work against adaptive updates. Because when you are sampling, your sample probability, like the adversary can see whether you sampled a row or not in the previous iteration, and that could change their decision of what is the new row that you wanted to put, and that can make it hard. Okay, does that answer your question?
I think I was wondering if there's already something that needs to be managed in the Oblivious setting because of how your probabilities, which determine what updates you make, depend on the JL sketch, but then you sketch a new thing based on these updates.
Oh, so I think it's fine because the JL sketch can work for unfixed vectors, and you can think of all the vectors that you have for all the iterations are all fixed.
Yeah. Okay.
But it will be a problem. But since we renew this GL anyways, so it's fine. Like this part doesn't really lose anything. Yeah.
So do you have to renew the sketch when a row is included or whenever you toss a coin?
Whenever a row is included, when you just toss a coin, you don't do it.
Well, yeah, so is that obvious when you toss it? Like if I tossed a coin but it failed, doesn't that change the conditioning? Why is it obvious that you don't need
Yes.
to refresh the JL sketch at that point?
The reason is because the JL sketch is an overestimate. So even you can consider we do this algorithm with another ideal algorithm that use a new JL sketch in every single iteration. And whenever this ideal algorithm doesn't sample any row, our true algorithm also doesn't sample any row. And once you don't sample any row, you just leak this binary information to the adversary of this is just a 0 decision or a 1 decision. And when you are not sampling any row, our algorithm will perform exactly the same as this ideal algorithm that renews the JL sketch in every single iteration. So we're not really leaking any information, so that is fine. But once we sample a row, we could leak in some information just by this binary decision, because there could be situations where sampling a row, but the ideal algorithm is not sampling a row because we are an overestimate. But when that happens, we just immediately renew the JL sketch. So that is also fine because we just don't reuse it anymore. Yes.
Sorry to ask another question, but yeah, is it clear like which step of the so I thought in the online leverage score sampling framework you're only using like 2 facts. One is like that they're always overestimates, and one is that the sum is always bounded.
Right.
The second fact is like clearly just always true.
Right.
The first one I guess like is where you would be worried for adaptive updates, but I would have imagined like in each step you're still independently sampling. Like, is there like an obvious counterexample why that?
Why it's harder?
Yeah.
The reason why it doesn't work is not like any of those parts. It doesn't work is because when you are trying to prove leverage score sampling gives some subspace embedding, some spectral approximation of the matrix, that proof itself doesn't carry over for adaptive updates. That's actually what I'm going to talk about on the next slide, so I hope it will make it clearer once I go over this. Okay. So on this slide, I'm exactly going to answer that question. Why isn't it obvious that leverage score sampling it's hard to make it work for adaptive updates? Why? Let's go back to answer this, we need to go back to the proof of why leverage score sampling will give you some subspace embedding. So let's recall this is the leverage score sampling. We say that we sample it and we'll get some subspace embedding. And what is the normal standard proof for this lemma? The standard proof uses the matrix Chernoff bound, which just basically says that if I have a bunch of independently random PSD matrices, x1 to xn, and they all have some upper bound, then we can know that the least eigenvalue of the sum of all these independent matrices, the probability that this is at most 1 minus epsilon of the expectation of these random matrices. This is bounded by like some exponentially small probability. And we can also get a similar bound for the largest eigenvalue. And now when we're proving the leverage score sampling lemma, we will define the independent random matrices as the rank 1 matrix of our row. So depending on whether you sample a row or not, yeah.
There are people talking during your talk, and it's making it really difficult to hear you.
Are there any questions?
I have a question in a minute, but go ahead.
Yeah, okay. So we define our random variable matrix as a rank 1 matrix, and then we apply the matrix Chernoff bound to it. But we can't just apply it directly, because if we just apply it directly, they only give us some bound on the least eigenvalue or the largest eigenvalue. But we can use a very simple trick by scale our random variable by the expectation. So now, after we do the scaling, the expectation of the scaled version would just be identity. So if you have some bound on the least eigenvalue and some bound on the largest eigenvalue, this will give us a bound on all the eigenvalues because this is just identity. And this proves the spectral approximation of the matrix. And that gives us the approximation property that we needed. Okay, so what about we just use this for the adaptive updates? Well, for the adaptive updates, we also have some similar adaptive matrix Chernoff bound. But here, the key problem here is that in this lemma, the weight matrix, sorry, the expectation matrix W, it's not a fixed matrix anymore. By definition, this matrix itself is a random variable. So it's the summation of all the xi's conditioned on the previous matrices. So this X, so if you just look at one term, so this expectation itself is a random variable that depends on what you're conditioned on. So it depends on this x1 to xi minus 1. And now in the lemma, because this W is a random variable itself, in the lemma we can only show that for any fixed value mu, the probability that the least singular value of the summation is less than 1 minus epsilon times mu, and the probability of this random variable, that is the expectation, is larger than mu, is smaller than some exponential probability that depends on mu. Okay. So the key thing is that W is a random variable here. And because W is a random variable, we cannot define the scaled version anymore. It's not even well defined. Why? Because W itself depends on whether we sampled the ith row or not. So it depends on xi. So this thing is not even well defined anymore. So we cannot do what we did previously in our previous slide for the Oblivious case. But what we can do is that we can guess what is the value of this expectation matrix W. So basically, we can use this bound for 2 to the d squared number of fixed values, and then still prove a similar concentration bound as before. But because we will need to guess over all these possible values of the matrix, and we wanted to sum them up by using a union bound, so we need a much smaller success probability, and that's why we will need to increase our sampling probability, because sampling probability actually have a log 1 over delta term in it, so we need to increase it by d squared times log kappa. This is one way that we can prove it, but that's not what we showed in the paper, because we have some way better that only lose d times log kappa compared to d squared. Okay. Are there any questions for these two slides? I think it is started. Yeah.
Do you know whether just like the exact same algorithm as online row sampling fails?
We don't know. That's a great question. We don't. I think this is a very interesting open problem. We saw it for a little bit, but don't have anything. Whether there exists any lower bound that separates the Oblivious case and the adaptive case.
Okay.
Right now, it only fails in the analysis. It still exactly the same algorithm. We just need to increase the constant before the sampling probability. Yeah. Any other questions? Okay. So next, let me go to what we actually do in the paper and how we actually get this d times log kappa. Okay, so this is the lemma that we proved in our paper. We show that we have the rows from A1 to AN, that's an adaptive sequence. And then we sample the ith row with some probability that's proportional to the online leverage scores, but with some factor C here. And then we prove that D is a subspace value of A. So our paper is based on this previous result by Biberman et al., but they have a linear dependence on kappa. So let me first talk about their proof ideas. So what they show is that instead of proving the spectral approximation of the matrices, they reduce it to the scalar case to just prove the L2 normal approximation for some fixed vectors V. And they need to prove this for all V's in some epsilon net. And the size of the epsilon net is roughly kappa over epsilon of order D. And then by using a union bound over all the V's in the epsilon net, they will need to have an actual dependence of log 1 over delta. And log of this thing is roughly D times log kappa. I'm hiding some like log 1 over epsilon here. Okay, and this is also the reason why we lose a D times log kappa factor that exactly comes from using this union bound for the scalar case. Okay, but their algorithm not only loses this factor, they also lose another kappa factor. And the reason that they lose the other kappa factor is because now we can define our scalar random variables for a fixed vector V. And ideally, we would like to prove the sum of all these error terms for every row is bounded by the sum of your final exact norm. So they're bounded by some epsilon times your final matrix times V. And then they use some scalar version of the concentration band for adaptive updates. And this scalar version also only hold for some fixed value mu. So you can show that the probability that this thing is larger than some fixed value mu is bounded by like exponential function of mu. So ideally what we would like to do is we would like to set mu equals to this bound that we want, and we directly give us what we want. But this is similar to the matrix turnoff bound case. This norm itself is a random variable because it depends on what are your future rows, and what your future rows could depend on whether you sampled your previous row or not, because the rows are given by some adversary. So what they showed in their paper, they just use a naive bound to bound this upper bound by the singular values, and that's why they lose a kappa factor. And what we show that is similar to what I described for the matrix case, we also guess what is this random variable. So by guess, more concretely, we means we build an epsilon net over a line segment that's all the possible, that includes this norm. So it's the range of this norm. And then for any fixed value s in this epsilon net, we can define a truncated sequence. So we can define a truncated sequence, which I will call xs, such that it equals to the variable that we care about, xi, as long as up to the ith iteration, our guess s is still a good upper bound of this norm. And then for any of those truncated sequence, we can prove concentration now because we can just set mu to be epsilon times s squared. Now, s is our guess, so it's a fixed thing. And we can prove this for all s in the epsilon net. But then we again need to sum all the failure probabilities of all these guesses by using the union bound. And now we only lose a log kappa factor because the size of the epsilon net is roughly kappa, and then we just lose a log factor of that. Okay, and then that gives our upper bound for the adaptive case. So the first term is still the same as previously, but in the second term, because we lose a d kappa factor, so we will lose like to a d to the first times the log kappa factor here. Okay, any questions for this upper bound section?
How much is the dependency on epsilon here?
It's still polynomial. Oh, you mean like exactly? It's epsilon to
Yeah, so
the-
it looks like you have poly 1 over epsilon. Is it epsilon to the 5 as well here?
No, I think it's epsilon to the -4s because the number of rows that you sample is like.
So epsilon square you would lose, right? I mean, so where is the extra epsilon square coming from? For the epsilon net that you pose.
No, I think from the epsilon net we just get a log 1 over epsilon. So
Oh, that's true.
We don't
Actually,
really
yeah.
lose anything.
Okay, so where do you lose the extra? So are you going to argue that this is tight or the d to the 5 over the poly?
No, I'm not sure if it is
Okay.
tight or not. That's still open. Yeah, that's just what we get right now. But this is like, doesn't really matter if n is much larger than d.
Well, I mean, lots of questions whether it's larger or not.
Yes, yes.
When in real data would be very different.
Yeah, I do think this is a very interesting question, whether we can get a same upper bound for the adaptive case or the Oblivious case. Yeah. Okay. So there are no more questions. Next, I will move to the lower bound part. Let me first state our lower bound lemmas again. So as we showed in the upper bound, our dependence on epsilon is polynomial. And our first lower bound basically says there is indeed a separation between the high accuracy regime and the low accuracy regime. So we can't possibly get more than d squared, better than d squared amortized update time if we wanted to maintain a very, very good approximate solution. And the second separation is between the fully dynamic case and the incremental case. Okay. And all of our lower bounds are based on this OMv conjecture, which is a pretty widely used conjecture in fine-grained complexity. So, in this conjecture, we consider the online matrix vector multiplication problem. So initially, we're given some matrix, some Boolean matrix M of size d by d. And then in each iteration, we're given a Boolean vector vi. And the algorithm needs to output the matrix vector product, so M times this vector v in the ith round. And the conjecture states that there is no algorithm for this OMv problem that we can allow it to have polynomial preprocessing time. There's no algorithm that have better than d squared amortized query time in each iteration. Okay. And you think about it, if we can have all these update vectors in the beginning, if you give them as a batch, then we can use fast matrix multiplication to get something that's faster. So basically, this conjecture says if you don't do that, if you give them one by one, then all this multiplication will take d cubed time. So high-levelly, this conjecture just says that the only way to speed up matrix vector multiplication is by batching these vectors together, and there's nothing better we can do if they're all online. And this is a unified conjecture that can be used to prove many conditional lower bounds for dynamic problems. A lot of them are shown in the original paper that define this conjecture. Okay. And it also holds if we have a number of queries instead of just d queries, and that's the version that I will use in our lower bounds. Okay, so next, let me show you a roadmap of how we prove our lower bounds. So we start from the OMv conjecture that says this OMv problem will need d squared time. And we first reduce it to a still OMv problem, but for real valued matrices that allows a 1-over polynomial approximation error. And we also reduce it to a projection version, where the matrix is some projection matrix. But this is not very important. This is more for technical reasons. So we first reduce this, and we say that in order to just get a 1-over poly d approximate solution for this real valued OMv problem, it will take d squared time. And then from that, we can directly reduce to the 1-over poly n approximate incremental least square regression, because here the approximation error is very small. But in order to get this constant approximation lower bound for the fully dynamic least square regression, we need to start from some hardness result that also have a constant error somewhere, even though the first term is a relative error, while the second term is an additive error. So the main technical, the key lemma of all our lower bound proofs is actually this proof here, to have some hardness amplification that shows that even if you wanted to have a looser approximation, that's a constant relative error, it still will need d squared time. So this is the key lemma. Okay, so next, let me see, I have 10 more minutes. I will quickly go through these two steps, just cover some high-level ideas, but not go into the details. And then I will go into more details of how we prove this key lemma, because I wanted to give you the statement of this lemma, and I hope that it will also be useful for some other maybe future research for other conditional lower bounds. Okay, but let me start from here. Okay, so now we wanted to reduce, so let me first give you the statement of this 1-over poly d approximate OMv problem. So here we assume that our matrix have real values instead of just Boolean values, but we need to assume that it has constant eigenvalues. So we need to assume that all the norms are constants. And we also assume that the query vectors all have unit norms. And then we want the algorithm to output some vector yi that have a 1-over poly d additive error comparing to the exact solution. Okay, and this problem will take d squared time if the OMv conjecture is true. Okay, so now when we're trying to prove this step here, we will assume that we have a very, very good oracle for the incremental least square regression problem. We assume it has a 1/n times some polynomial of d approximate solution. And we wanted to use this oracle to compute some vector yi for this OMv problem. That's how the proof goes. So we construct the least square regression instance such that our initial inverse matrix equals to the matrix M that we want in the OMv problem. And then we add some row AI, that's the query vector, but scale it down by n times some polynomial of d. And because we scale it down, so this vector will have a very, very small norm. And it's very important that we scale it down by something that's n. That's why we only get like this hardness result for 1/poly n approximation. Because of that, then all these rows doesn't really change our matrix at all. So even if we add all these rows, the inverse is still up to very small error, roughly the same as our initial matrix. And then by the Woodbury identity, the difference between the two LSR solutions will exactly give us the matrix vector product of M times this AI. So now we can just scale up the difference between these two as our solutions and use that to recover some approximate solution for our OMv problem. Okay, any questions for this slide? Yes.
So at the end, you round these vectors because you know the vectors you received were binary.
Yeah, so basically you are trying to design an algorithm for this problem, and then you just call the oracle in each iteration. Yeah. And from the oracle, you will receive some solution for the least square regression.
But you get approximate answers, right? And then you need to round them to.
Right, there are some.
Right, you're using the integrality of the OMv conjecture.
Yeah,
here.
there are some running, yes, in this part. Yeah.
Thank you.
Okay. And then next, let me go to the second step where we reduce from this stronger hardness result to the constant approximate fully dynamic least square regression. I will only be able to cover some very high level ideas here because this is a little more technical. So similar as before. So we wanted to solve some online projection problem where our matrix is a projection matrix, and then we wanted to output some vector that have some constant relative error and then 1/poly additive error. And now we assume that we have a constant approximation but fully dynamic least square regression oracle. And this fully dynamic least square oracle is more powerful in the incremental oracle in the sense that in our reduction, we can still add a row that's some scaled version of the query vector in the ith round. But after the ith round, we immediately delete this row. And then in the next round, we get a new row, and then we delete it once we recover the solution. So that's how we use this. That's why this is important that it's fully dynamic. And I'm hiding a lot of details, but similar as before, the difference between our solution in the ith round and the initial solution will roughly give us m times the vector that we care about, but with some constant error. And because we get some constant error here, it's very important that we need to reduce from some hardness result that itself has allowed some constant error. Okay, so that's why we need this stronger online projection hardness result. And that will, let me see. So that will be what I will talk about now. So now I'm ready to define this online projection problem more rigorously. So in the online projection problem, initially we're given some projection matrix that will project a vector to the subspace of denoted by U. And then we're given a sequence of unit vectors as the query vectors. And then I will use this notation, V with subscript U, to denote the component of the vector Vi projected to the subspace U. And the algorithm needs to output, there are two different types of approximations. The stronger type is we only allow 1/poly d additive error, where some Yi, the difference between Yi and the exact solution is bounded by 1/poly d. And a looser approximation is where we still have a 1/poly d additive error, but we also allow a constant relative error. So it's some constant times the norm of the exact solution. Okay, and the hardness application key lemma says that if we have the hardness result, that there is no d squared time algorithm for this 1/poly d additive error online projection problem, then we also know that there is no d squared time algorithm for this 1/3 relative error online projection problem. Okay, so how our proof is going to go is we will want to solve this online projection problem to this higher accuracy, but we assume that we have some low accuracy oracles. So we assume that we have two oracles, one that projects the vector into the subspace of U, and another one that projects the vector into the subspace of the orthogonal component of U, which I will denote by this U orthogonal. And we will use polylog number of oracle calls to these two oracles in order to recover a vector that has a higher accuracy. Okay, so how do we do? The first attempt is as follows. So we're given some vector V, and then we can decompose it into two orthogonal components, one in the subspace of U and one in the subspace of U, orthogonal space of U. And then we have this more loosey oracle. So the first idea is in each iteration, we just use this lossy oracle to compute the component, but with some error. So we just project V into this orthogonal space to compute some vector W, but this W will have some error. And then we remove this component. So we compute V minus W. So this V minus W will be closer to VU. And then we can continue this for log D times. And then so that the component in this orthogonal space is smaller and smaller. It starts from some constant, but after log D times will be 1 over poly D. Okay, so like we do this again and again. But there's a small problem with this first attempt. The problem is that when we're using this oracle to compute some W that approximates the component in the orthogonal space, it will introduce error in both directions. It will introduce error both in this orthogonal space and also in the space U that we care about. So in the end, we will get some vector that is almost completely inside U, but this vector will have some error that's more than polynomials. It will have some pretty large error, and we need to remove that error. So what we do is that we use what we showed on this slide as a black box and do another level of reduction on top of it. So what we've shown is that we know how to compute some vector y that's approximately to VU, and it has nearly 0 component in this orthogonal space. But on the other hand, we can also reverse it. We can also compute some vector W that is almost completely in the orthogonal space, and it has no component in the space U. So instead of just using one oracle call to the projection oracle and compute this lossy vector W, we instead use what we showed on the previous slide and use this log D number of iterations to compute this W star that is almost completely in this subspace VU orthogonal subspace. And now we do what we did before. We again remove this vector. And because now we make sure that our error all stay in the orthogonal space, so it's fine. So we don't introduce any extra error in the space that we care about. And now we again repeat it for log D times, and then we reduce the constant relative error to 1 over poly D additive error. Okay. So that's all I wanted to say. And I also wanted to mention that somehow this is a little similar to the iterative refinement algorithms that Diksha talked about in the previous slide. So I think there is some intuition that could be the same between the lower bounds and the upper bounds. Okay. As a summary, what we talked about today is epsilon approximate dynamically squared regression problem. And we showed a OD upper bound when we only want constant approximation, and then we only have incremental updates. And we show lower bounds that says that we can't really improve these two conditions. These two are both necessary. And let me list some open problems. The first one is right now, for adaptive incremental updates and for Oblivious incremental updates, there's still a gap in the second term. And this only shows up in the analysis. The algorithm is still the same. So we wanted to know if we can improve this term. And the second problem is all this only works for the most simple L2 regression problem. And then I don't know any algorithm that works for the harder LP regression. And then for the lower bound right now only works for fully dynamic and adaptive setting. We don't know anything about fully dynamic and Oblivious setting. And finally, I think this constant relative error online projection oracle lemma could be interesting on itself. And then I wonder if there are other reductions that can come from this harder constant approximate hardness below. Yeah, that's all. Thank you.
Thanks a lot for the talk. Can you tell us briefly so the lower bound for fully dynamic works only for adaptive updates, but can you say when did you need this?
Yes. Sorry. So it's here. So when we call the oracle here and then remove this and then use this new vector as a query vector for the oracle again. So it's very, very adaptive, all this proof here.
I see, thanks. Yeah.
Is there a reason you didn't look at decremental settings?
We just didn't look at it because our intuition started from this continuous ML where you're always collecting new data. So,
Okay.
but I think that's an interesting open problem as well, whether you can have something for the decremental model. I don't know anything about it.
Thank you.
You gave a quick comment on the randomization. Is there a hope for deterministic algorithm for that?
Yeah, that's also a great question because if you have some deterministic algorithm, then there's no issue of adaptive updates anymore because it works for both of them. But I don't really know because now the upper bound heavily depends on the sampling algorithm. We know that if you are static, then there's some way to compute. You don't really need to do sampling. You can use the deterministic algorithm to keep some rows. But I don't know how to make that dynamized. It seems very expensive.
Do we even know static algorithm that is deterministic and has running time ND?
No, I think you can sample the same number of rows, but the running time is much larger.
So it means like the barrier for deterministic dynamic algorithm is even in the static setting.
I think so in terms of running times.
Yeah.
I think you said this, but I lost it. So is this approximate projection thing, this conjecture is implied by the normal OMv conjecture, or it's like a different conjecture?
Oh, this is implied by the OMv.
Okay. And then like
all the reductions.
related to this, like why were you able to assume that you had access to both U and U perp?
That's a good question because in the OMv conjecture, it would also hold if you allow polynomial preprocessing time. So where in the preprocessing time, you can just compute the orthogonal matrix as well by using like e to the omega time.
Oh, I see. So it's like you're taking you have some initial matrix and you.
Yep, you have the
Anyways.
initial projection matrix, and then you have many queries. Think about this like a large polynomial of D, but you allow yourself some polynomial preprocessing time. It's still hard in the conjecture.
Okay, cool. Awesome. Thanks.
Anybody else?
Well, I guess if you have no more questions, then we thank the speaker again.